Good morning. Welcome everyone to our DAMSI seminar. Today's speaker is Dr. Piotr Przymus, and the title of his talk is Advancing Code Quality through Mining Software Repositories. Piotr, the floor is yours.
Okay. Thank you very much for having me here, and I will try to lead you through the research that we did with my colleagues. So I will start with the team. We cooperated on those projects with Mikołaj Fejzer, who was a PhD student, now a PhD, and he was studying here at our university. Now he works commercially, but still cooperates with us. With Jakub Naremski and Professor Krzysztof Stencel from NIM UWO, and of course me. And I will start by deciphering some of the parts of the title. So let's start with the software quality. I actually like one sentence that summarizes the software quality, that it's basically quite hard to define, usually impossible to measure, and quite easy to recognize when you see it. When you're a experienced programmer, when you see a code, you usually can quite easily tell if the code is of a good quality or not. But because of those problems, we'll try to concentrate on very specific aspect of code quality. So we'll try to discuss how to deal with buggy code, so bugs in code, so problems in code that at some point can lead to a problem with the software. So in extreme scenarios, an application like a bank application can have a bug or problem that can be used by someone else, and for example, to steal money. But there also can be some pretty trivial or small problems that can that might need fixing. So basically, bugs are quite serious problem in code development, because a lot of resources that we will spend on developing code will go into containing and fixing bugs. And there are some estimations that even 1/3 of software development cost will be actually spent on bug removal and bug prevention and so on. So basically, this is a quite serious aspect of software development: how to deal with bugs, how to prevent the bugs, and what are the reasons that the bugs occur. So now let's go to the mining of software repositories. So basically, this is a subfield of software engineering and data mining. So we'll use here data mining techniques in the context of software engineering artifacts, and try to develop useful for developers instruments useful for developers that can help them create more safer code, or to deal with some problems with the code. So basically, we are dealing here with rich data. So we have a lot of sources of data, and in a moment I will show you what are the sources. And usually developers will use those tools that will allow us to get those kinds of data. There's a lot of trends inside these subfields, but the main are like concentrating about the quality of the software and support of the programmer's work. There is also a quite important aspect of examining the interactions between interactions that take place inside the development of a project, because in many cases, software development is not concealed to a small team. It's usually a team of often tens or hundreds of developers that will have to cooperate. And because of that, there is a lot of interactions going on, and those are not non-trivial, and also observation made from those interactions can help to structurize better projects in future. So immediate applications of mining software repositories are software bug prevention. So in those approaches will try to prevent bug from being released into the software. So all of the approaches that will try to localize bugs in the software. But there is also localization of bugs based on some user bug reports. So in this scenario, we try to, based on some description that user gave us, we try to find files that possibly are suspected of having a bug inside. But there's a lot more like code inspection or even code completion, suggesting what parts of what developer can put next into the project, and so on and so on. And of course, there are also the social aspects. As I said before, software development is a collaborative effort, and in many cases, we'll have hundreds of developers that will cooperate. And the idea here is to create tools, but also check how the interactions work and try to optimize them and try to optimize the workflow of the software development to have like to optimize the costs that are needed to develop software and so on. So we have a vast sources of data. Many projects will be developed using different tools, and those tools will leave artifacts behind during the process of software development. So most of modern software development will use some form of version control systems like Git or Subversion. And basically, this is like a standard. So people will use this tool to version the code during the development process. Then, of course, we have all the information that we can get from the source codes, all the meta information, the project file. But also we can actually, this is programming language. So if it's a code written in some programming language, then we can analyze it on some lower level. We can see how the abstract syntax tree looks. We can go into assembler and so on. But there are also aspects related to maintenance of the project. So there we have systems that will allow us to track bugs or issues connected to given software. We have software that will help us to develop the project. So if it's a collaborative effort and it will take years to develop, then we have software that will help the teams to organize the work around it. And then we have the various forms of communication. We also have systems that will allow us to improve source code review. So basically, in this scenario, the source code before it's committed, or even before it's included into the main branch of the software development, will be reviewed by some independent reviewer within the project that will assess the quality of the code before it's actually included. And we have many other sources. So from one side, on one hand, we have like a very rich data set, but on the other hand, it's not always that clean kind of data. So basically, there a lot of times we will have some aspects of the project described in given source of data, and while there is some structure to the data, we have to treat it as a semi-structure, because not always we'll have a structure inside of the data, and sometimes we have to come up with the structures ourselves. And what is more problematic, it's that this everything evolves in time, so it will change in time. So this makes it a quite interesting problem, because we have a lot of data. The data is semi-structured, not always clean, so we have to deal with that, and it will change in time. And in next slide, I will show you a visualization just from one source of the data, so from a version control system. It's a visualization of a project that we developed inside our team. We had only 4 developers, and we developed it. It was a software developed for one of the papers, and it took us something around half of the year. And you will see how the interactions, even in such small team and on such small project, can look like. And you can imagine that in more complex projects, it will look more, it will be much more complicated. So let's see the visualization. So here we have developers that create files. The edges are directories, and the leaves are actually files. And we can see how the interaction looks here. So we have 4 developers that touch different files, modify different files, cooperate on different aspects of the project. And here we see what type of files actually were created. And as I said, this is very small project developed just for, this is a software developed for one paper, and it was just half a year. And real projects, so let's say big commercial projects or even big open source projects, can have teams with thousands of developers and years of development. So those interactions gets complicated and are much more complex. So, okay, what are the motivations? So we'll try to use the mining software repositories techniques to elevate code quality, various aspects of the code quality. And in this talk, I will try to discuss 3 aspects that we actually were involved in. So first, I will start with life cycle of vulnerabilities. So I will talk a little bit about some serious bugs that can actually be used to break security of an application, and how people deal with those problems. And then I will show you a system for bug localization that we developed. And finally, I will talk a little bit about how we can assign reviewers to code fragments and to let's say improve the process of finding reviewers for code review. So let's start with the lifecycle of vulnerabilities. So in this part, we'll concentrate on something that's called CVE. So here you have this part, CVE. So basically, CVE is a system for describing vulnerabilities, common vulnerabilities in various software projects. Basically, it's a way of creating an identifier for such a bug or problem. We'll have some description of the problem. We have some systematic way of describing what is the type of the problem, what is the score, or let's say how serious the problem is. We have various vectors that will describe, I'll try to characterize the vulnerability. And we'll have some additional information, so like a more detailed description of the problem. We have some hyperlinks that will lead us to various sources of information about this bug. And we also have some enumeration system that will enumerate type of problems that can be found in given bug. So yeah, so this is the system. So it actually, at the beginning, let's say when we started to develop the software, we quickly realized, let's say the humanity quickly realized that bugs are something very common, and there was like there were many approaches how to track the bugs, and there were like different companies or organizations that tried to make the process of tracking the bugs more straightforward. In the end, now we have a standardization that it's the CVE system, and it's basically a system that allows us to easily identify a bug, easily describe it. There is some rules that we have to follow when we try to describe the bug. But in the end, it simplifies communication. So basically, the main goal is here to simplify the communication and make sure that all parties involved in software development are what's the problem related to their software and how can they deal with that. So basically, it's quite important system. It's financed by U.S. government, and basically the one part of this, so the CDE list that is provided by Mitre organization or community is sponsored by Department of Homeland Security, and there is a second system basically that extends this list, and they are supported by National Institute of Standards and Technology, also a government institution. And basically, so this is a organization that is supported by government and will track the bugs, but all of the bugs that can be added to this list are actually added by some subports of this organization. So basically, different kinds of software will have like a specific subpart that will deal with specific software and bugs within this software. So to make it more concrete, for example, companies like Adobe can be one of. Actually, Adobe is one of the sub-organizations that will track bugs associated with Adobe products, and basically they are part of the bigger community here. So okay, so now that we know what are the vulnerabilities, I will go to the research. So basically, this research was done as a part of a mining challenge that was organized last year. So in 2023 year, there was a mining challenge for mining software repositories, and the problem there was that there was a very big data set of software development interactions, and the goal was to find some meaningful information on this data set. So basically, our idea was that we will combine the information that are stored in the CV system with the information that we can get from the interactions between developers on various projects, and try to characterize how developers will deal with problems over time. So a little bit about the data set that was valid for the challenge. So basically, the Word of Code, it's a project that is developed for quite some time. So this was, I think, fifth version of this project. It's actually a quite big project where they store a large number of Git repositories with vast majority of number of commits and a lot of trees and blobs of data that can be stored. So basically, this is all scraped from the network. So basically, they track all open source projects and basically gather all of kinds of information that they can get. So this actually allows us to get a quite nice access to the different kinds of data that can be associated with the projects in one place. The problem is that it's actually quite big. So basically, the entire data set is this size. So to use this data set, actually, you cannot just download the data. It's not feasible. So we had to basically all of the teams got access to the cluster that is located somewhere in Texas. And basically, we had to at least prepare some extract of the data on the servers, and then we could follow up in our own infrastructure. But yeah, this is quite a large number of data. So basically, to process it or even to get some meaningful information from this one, we had to use a lot of techniques that are associated with high performance computing to actually be able to get the data in reasonable way. So, okay. So now that we know what vulnerabilities are and what kind of data we got, we can go to the research questions that we tried to answer. So we stated 2 research questions. One was about what type of characteristics what kind of characteristics we can spot about CV lifetime within a project. And second research question was what type of factors are affecting the lifetime of the CV in a project. So basically the idea here is that, okay, bugs will occur in the software. There is a system that will track the bugs. And so basically we know about those bugs. We have information about development of the software. So basically we can probably spot the moment that the bug was fixed in the software. So we can try to assess, are there any specific factors that actually influence how fast the bug will be fixed? So the idea here is that we usually would like that the problem that is listed in the CV will be fixed in the software as fast as possible, because otherwise the users are still are subject to some problems with the software. So we'll consider different characteristics of the both programming languages or some unique features of the CVs and characteristics of the projects. So yeah, a little bit about the pipeline. So basically, we had the word of code. We had the data sets from the CV system, and we had to combine it. So basically, we wrote our pipeline that combined all of the information. The visualization that you saw at the beginning was connected with developing this pipeline for this paper. So basically, yeah, it took a little bit time to connect the dots, but in the end, we found at least this number of projects that were actually vulnerable. So there were connected to the CV listed in this database. And for the purpose of limiting the data set only to cases that are explainable, we just selected the projects and the bugs that were actually fixed within 1 year from the publication date till the fixing time. So basically, here's the number. So in the end, we analyzed around 62 and 866 pairs of projects and CVs found in the dataset. So, okay, a little bit about the CV lifetime. So basically, what we actually are measuring, because we cannot measure everything. The problem is that CV is basically a system that will allow us to track the CV by the CV number. So basically, it has to be assigned. And the bug in the software can actually occur somewhere in the past. So basically, it's not that there is a bug and immediately we know that, okay, this bug needs to go to this system and then we get the ID. It's usually that someone introduced the bug, people didn't know that it's a bug. At some point, someone spotted that, okay, if you have some strange conditions on running the software, then you can exploit the bug and then you can, for example, break the security of the application. So basically, it takes time. And this part is usually unobservable because it's pretty hard to assess it automatically. But at some point it was introduced, at some point it was discovered by someone, and usually the one that discovers it will try to create a entry into the CVE system and say, okay, I found a serious bug in your software, and basically we need to give it an ID, and I will then give you some details, and please try to fix the bug in the software. So yeah, so usually what we can actually observe is the starting from assigning the CV ID, then there is a public publication of the details of the CV. Sometimes we'll get the CV ID and the publication of details at the same point. Sometimes there will be some period called embargo. So basically, this period called embargo means that the bug is somehow serious, and the developers are given some time to deal with fixing the bug before it goes public. And this is like it's actually quite important that the bugs will be at some point become public, because the practice shows that if a company gets information about the bug and the information is not going to be public, the companies not always will fix the bug immediately. And there are cases with big companies that took like years, 1 year, 2 years, or 3 years to fix the bug that was at some point found, and they had the information that there is a bug in their software. So basically, this is like we have to like find a good proportion of when do we go to public, and we have to at some point go to public. This is like actually a good practice to go to public with the found bug, because otherwise the company might not fix the bug on their own without some additional motivation. So usually if there is embargo, usually the embargo will be like something like 100 days. So around 100 days, the developers will get time to fix it. Sometimes there can be some extension of the bug, but this is the reason that CVE ID can be assigned before the CVE publication. And then after the CVE publication, or even before, the developers have time to fix it. So basically, it's also a good practice that developers will fix the code and they will put in the commit message, so the meta information about the code, they will put information that I'm fixing this CVE ID in the software now. So basically, we can usually track the information if it's when it was fixed and so on. So for the lifetime of CVE, we'll say that we have the date of creation of the CVE. So basically, what we can observe is the minimum of the date that the CVE ID was assigned, or the publication date of the CVE. So this is our starting date and the date when it was fixed. So basically, this is the last date, last commit that we saw in given project that fixes this CVE. So we can actually try to analyze the lifetime defined like this way. So what we will use for that? So we'll use here survival analysis. So basically, survival analysis is quite known approach in health, biology, but also in project failure and so on. So basically, we'll have a function. We'll have the probability that up to time t, the event of interest did not occur. So we'll basically measure how long it takes different bugs to be fixed in the project. So we'll say that CVE died at the point when it's fixed in the project. And to do that, we'll use the Kaplan-Meier estimate of the survival function. Basically, here we count the number of events that, in this case, of CVEs that were fixed in the project, and here are all of the CVEs that are still active in projects. And also we'll use the XE Summers D measure, and this one will allow us to measure which factors are actually more important than others in terms of differentiating how much the given factor impacts the survival rate of CVE. So okay, so let's start with some general statistics. So basically, the mean time of fixing is around So basically, in most cases, the fix will be done in one commit or 3 commits. So vast majority of projects will actually be fixed. Will fix CVE within 3 commits. in many cases, there will be embargo. So basically, here we split the data into the cases that we actually knew that there was embargo on the on given CV, and we know that most of the projects were actually fixed during the embargo. Some of them were fixed after the embargo, and this part, no embargo, basically means that we couldn't distinguish if the fix was within embargo or not because of various factors. And if we look at the survival rate, so it's not bad if the information goes into the CVE systems. CVE system, usually the software will be fixed within 34 days from the time it was found. So it's quite reasonable. In terms of how the projects are developed and what type of languages will be involved in the fixing. So basically, this plot actually shows us that most modern software development projects will involve multiple languages within one project. So the project is developed in more than one programming language within a project. And there is a lot of, so this basically means that often when we fix codes, so fix a bug in a given project, we'll have to fix it within, for example, C++ language and, for example, with Python language. So there's a lot of cases that basically, or I would even say that most of the cases we will have to use multiple programming languages to actually fix a bug within a project. So yeah, about the risk factors, there we actually measured the risk factors. So basically, here you have the DXY Summers D measure to how important the feature is. So basically, what we can see, so that the lower, so we actually look at the absolute value of this one. So the higher the absolute value of this one, the more important feature is. So I will just show you some most important aspects here. So basically, one interesting part is that type checking, so static or dynamic type checking. In terms of fixing time, usually when we use languages with dynamic type checking, usually we can fix bugs faster. Probably this means that we are dealing with different kinds of bugs. So basically, when we are in the static field, basically most of the static problems can be solved by, or trivial problems can be solved by a compiler that will say, okay, you have a problem with the type. But then there are those series, the other series of bugs that will actually take some more time. So probably this is the reason. Then we have the memory model. So basically, this is like in accordance with the intuition that basically when we use managed programming languages, we will fix bugs faster than in non-managed cases where we have like a lot of different factors that can influence fixing time of the bug and so on. So this is the highest influence in the programming language characteristics. Then we have the CVE characteristics. This one is actually interesting because there is a score assessment in the CVE system that basically tries to assess how serious the problem is in the software. And basically we can see that while there is a difference between critical and low, so basically if the bug is assigned as critical, it will be fixed faster than those with low score. But there is not much difference between medium and high. So basically, people treat medium and high the same way. So in terms of the fixing time. Yeah, and the highest influence was for bugs that for the way how the bug can be actually accessed. So bugs that can be exploited using the network connection are with the highest risks. Those are with the highest risk, and usually people will fix them faster. And the ones with local, with the scope of just of a local machine, are not as important, and they will usually take a little bit more time, just because the network ones are usually more important. And the third one, and actually the most important one, is how the software is developed. So basically, here is an argument for not creating so basically, if we have too many developers involved in a project, then time to fix the bug will take considerable larger time to fix. So basically, if we have very large projects like Android operating system and so on, basically there are thousands of developers that actually are involved in the process, and this does not help with fixing bugs. So usually smaller teams will be able to fix the bugs faster. And the same goes for core developers, because here we had like all of the developers that were involved in the project, and core developers are developers that actually do the main part of the job on the project. So they are usually hired to work on this project. So this is the same here. So basically, smaller teams will usually work faster, fix faster bugs compared to larger teams. And next interesting part is basically the number of files, which is also quite good factor for complexity of the project. So basically, the more files we have in the project, the harder it will be to fix the project. So yes, and one of the next the last important factor here is the number of active nodes. So basically, when we start a new project, usually we'll take some dependencies, so we'll use some other libraries or projects that are actually developed. And one good factor to assess which library to choose in our project is to look at the activity of the project. So basically, projects with longer time of active development will usually faster react to problems with security within their software base. And so this is one good reason to actually select popular libraries that are actively developed, because usually they will fix bugs faster. So yeah, of course, this is a large-scale study, so there are some threats to validity. One of the threats, the observability of CV in a project. We actually depend on developers that they will use the CV ID when they fix the bug. So this is like one of the important factors, problems that can occur. And then we have data quality. So while the word of code database is quite nicely organized, and they put a lot of effort to fix all of the missing data and some messy data, still there are some problems that can occur. We actually had to remove around 8.5% of projects just because there were some problems with the data. This is, of course, right sensor data. We cannot we can just observe when some points of time. So this is the reason. This is the right sensor data, and there are some other threats to validity, but not as important. So I can, if you have questions, I can later answer to it. So basically, this is the first part. So this paper is already published. So we actually got a second prize for this paper. And you can, if you are interested, you can actually get the source code and recreate all of the experiments that we did from this repository. Okay, so the main conclusions are basically that it's not that bad. When it goes to the CV, usually it will be fixed within 34 days. It doesn't take a lot of time to fix a bug, usually 1 to 3 comics, and in a lot of cases, the fixes will involve multiple languages. So, okay, now I will go to second part, so the bug localization. So basically, I will briefly tell you what's the problem here. So basically, when we have a software that is used by users. Users at some point will spot bugs in our software, and then they will prepare a bug report that describes what's the nature of the problem. Users can have different levels of technical knowledge, so basically those descriptions can be quite naive, or then they can go quite deep into the details. If we have enough information to deal with it, then it would be nice if a developer, based on the bug localization, based on the reported bug, could actually get information what files most probably are involved in this bug. So basically, what we want to do here is to rank project files, so the software files within a project, and say, okay, in those 5 files, probably you will find the bug that is described in this report. So basically, this is the main idea of this one. So basically, we are creating a ranking model for the files that are in software repository based on the bug report, and we return to the user files that are ranked in order of how probable is that the problem is actually in this file. So yeah, basically this is, as you can imagine, this is quite practical. There is a lot of research done in this area. When we wrote this paper we started in 2018. Basically, this was the how it looked. So we had a lot of teams, a lot of papers that actually describe how to localize the bugs. Yeah, those arrows actually spot how they compared between each other, because not all of the projects compare to each other. So basically, at some point we had a problem to which state-of-art method we should actually compare, which method is actually considered now as the state-of-the-art. So basically, we created this graph, but it was a lot of so there's like a lot of research done in this area. So in the end, this method is actually one of the top methods, and we compared ourselves with this method that was developed in this paper. And to summarize the graph that we had there, there's like 3 different kinds of approach that people use to deal with this problem. One was a similarity-based approach. The problem here was that usually it was not that the accuracy was not that high. So basically, those systems had a lot of problems and false positives, and basically they were not that usable. There's a large number of papers that actually use learning to rank approaches. So basically, here we use machine learning models to try to learn how to rank documents based on some factors. And also here you can actually utilize neural network approaches, but there are also like separate neural network approaches that basically use some other kinds of methods to try to get to the same goal as learning to rank methods. But basically, in a lot of those cases, the results were not that impressive, and they had a huge computational cost. So basically, what we did, our research was within the learning to rank approaches. So our goal is basically to create a function that will, for a given bug report and given file, return some value, some ranking that says how important the file is within the project. So yeah, we have to have some features, some data that describe the source code and the bug. So basically, we use a set of features that are computed based on the source code and the bug report. Those features are actually known from the paper et al. So basically, there are like 19 features, and we reuse the same features in terms of this project. One difference is that basically we found problem in the previous approach. Basically, they had a feature that was leaking information from the feature, and we actually contacted the authors. We discussed with the editors and so on. Basically, it was quite interesting experience, but finally, our paper was accepted with the information that there was some problems in the previous research from Ye et al. Even though we quite liked the approach that they did, actually they had some little flaws inside and so on. And we'll split the data in time fashion. So basically, we'll split into consecutive faults and trying to predict the localization of the bugs. So basically, to summarize, in terms of bug localization, there are like 4 major steps that have to be dealt with during construction of such a system. So basically, one problem is that there is a huge disbalance between the files that will need to be fixed compared to files that are not fixed. So to give you an example, usually a bug fix will require like 3 files to be modified, and we can have thousands of files in the project. So basically, this is one of the problems that we have to actually train the system on not all of the data, but we have to select the best examples of the data and show it to the system and then train on those examples. So basically, this is the reason for the first 2 steps, the initial ranking and imbalance handling. So basically, we have to initially rank the files to select the best examples, and then we have to limit the number of examples that we show. And the first major difference between the approaches that were before and our is that we have an adaptive scoring mechanism and adaptive cutoff mechanism to select the most important files that we will show to the system to train it. Then there is a problem of, let's say, tangled changes. So basically, a lot of times bug fix. So what we observe about bug fix is that a user or developer fixed some lines of the code, but we do not know how important this line was compared to other line that he fixed in this problem. So a developer can fix a bug and then write a test for that. And surely the code fixing is more important in terms of fixing the code than writing a test for this case. Still, writing the test for this case is important, but it's not the most important part of this. So basically, the previous approaches didn't distinguish between the importance of the types of changes that were inside the project. And what we actually did, we tried based on our model. So basically, our model tried to estimate how important each line of fix was, sorry, each file, because this is a file-based system. So how important fixing given file was compared to other files. So basically, we had some gradation of importance here. So this is the main difference between the systems, that we have actually the gradation. And based on this gradation, we actually use adaptive SDG regression, and our method falls within the pointwise learn to rank methods, which was actually first successful application of pointwise methods in terms of this problem. Because other approaches use pairwise or listwise approaches, which are usually more computationally expensive. And our is actually pointwise, which maybe is not the best in terms of learn to rank, but actually we got the best results compared to others. But it's actually quite easy on the computational resources. So yeah, basically we created experiments based on well-known data sets. So basically, based on the Ye et al. Data set and bug localizator data set, we used common metrics for evaluating rankings like accuracy, mean average precision, or MAP, or mean reciprocal rank. And basically, in terms of accuracy at case, so basically, how accurate are we in the top document that we returned, how important the document was compared to the original one, and so on. We, in most cases, are able to surpass the state-of-the-art method, so Ye et al. And here is, of course, also the let's say, the interesting part, because we really tried to replicate the results from Ye et al. We had some discussions with the authors and so on, but in the end, we could not replicate exactly the results. And the reason was because we actually implemented one of the features that did not leak the information from the feature. But at this point, the discussion with the authors of Ye et al. Was like cut off. And basically, we know that we present here the results that they showed in the paper, but basically we know that probably they will not be able to get those results if they use the proper feature. And we have actually computed this, recreated their method, and it will be actually a little bit lower than this one. And in case of the recreated method, we will actually beat all of the Ye et al. Results, and our method will basically be better. If we just look at the results that they mentioned in the paper, we are actually also better, but not in all cases. But basically, yeah, you can see that this is one of the cases that Ye et al. At some point is a little bit better than us, and here is the second point. But basically, on other methods, we are actually usually better. And second, so these are the results in terms of map and MRR. So basically, the underscored version is the best one. So basically, you can see that in terms of map and MRR, we are actually better than Ye et al. With the results that they actually showed in the paper. And compared to other models, it's still good. We actually beat on the second data set, we beat all of the methods with just one small hiccup here. So basically at accuracy at 10, one method is actually a little bit better, but just on accuracy at K at 10, and that's all. And in other cases, we actually we have quite better results compared to the ones that you can see here. So the higher here, the better for us. Yeah. So basically, we can actually deal with it quite well. So okay. Quick discussion. Yes, it's basically a first successful usage of the pointwise in back localization. It's resource friendly. It's actually quite efficient. Of course, there are some threats of validity, but basically the threats of validity are connected with the original data sets that we used. So most of the data sets were like monolithic in terms of language. And we know that some of the information were missing from those data sets. We actually tracked some examples that were missing. We actually also published extended data set that fixed some of the problems, but we use the comparison on the same data set just to make sure that we actually are comparing the same results to the same results. Yeah. And as usually, the code and data the paper is published, was published in 2021. It was online, and now it's in 2022 it was a paper version. And the code and data is also available at our GitHub, and you can recreate all of the experiments that you need. And the final one, and I will try to be very brief here, is the code review problem. So basically the code review problem is this is one of the ideas how to ensure quality of the code is that before a developer submits its code to the main branch of the software repository, there will be some third party that will actually look into the code and say, okay, I think this code is good, or you need to fix that, or I don't understand this one, and so on. So it's basically like a peer review of research papers, but it's done on a much bigger scale, because in big projects usually we can have thousands of commits, and all of those commits will go through some process of code review. So one of the problem in big projects, when we have a lot of developers, usually more than 10 developers, is that not many people will want to do the code review. and because it takes time, so basically they will do the code review, but it's not like some automatic, someone has to think, okay, I have to review the code and so on. So one of the ideas to improve this one, and it's actually in terms of, for example, of GitHub, it's actually used, is to suggest people within the project that can actually review the code, so that they might be interested in the code and they might have the knowledge to review the code. So this is a similar problem to how to find a reviewer for a good reviewer for my paper. It's how to find a good reviewer for my code that I wrote within the people that are inside the project. So yeah, we will try to suggest who should review the code, and basically there is some external research that shows that if we assign a reviewer or suggest a reviewer beforehand, usually the time for review drops significantly compared to time when there is no reviewer selected at the beginning of the process. So yeah, there were like different approaches in the literature. So starting from very simple tools, like tools that looked what was the last developer that touched this file, so modified the file, probably he will be a good reviewer, to some more complex one that actually looked at the, for example, modified meta information within the commit message and previous works on reviewers, to some very complex where actually some interaction graphs were created, and those graphs were analyzed in terms of selecting the best reviewer. So we tried to find a method that basically would outperform in terms of quality of recommendations other approaches, but we wanted it to be easy on the computational side. So basically, we wanted to find a method that will use not that many resources to compute it, because in the end, it's just a recommendation and it has to be done quickly and efficiently. So basically, that was the idea. So what we did, we actually created a approach where we created profile of a reviewer, and this profile is modeled as a multi-set. So basically, multiple occurrences of the same element in the set can occur. And so basically, we create the user profile as a multi-set or a bag of words of path fragments of modified files that he actually reviewed. And then when a new commit arrives and it has to be reviewed, we have to find a similarity between the user profile and the commit. And most of those traditional recommender systems approaches didn't work well for us. We actually used, as an example, Jacquard index to show that it may be problematic in terms of this case, in this case. But basically, Jacquard index works on normal sets, but we modified the Jacquard index to work on a multi-sets. But basically, it didn't give us either the normal version of Jacquard index or the modified version of Jacquard index. Didn't give us good results. But in the end, we decided to use a generalization of Jacquard index. So it's a Tversky index. So basically, this is a measure that allows us to compare prototype to a variant of given product. So this was the original idea of it, and basically it allows us to steer using alpha and beta. How important for us is to that we are similar to the prototype, or we are similar to the variant. So yeah, to finalize, we actually developed some other extensions of this approach, and also presents the results, and I can go in the questions to details of that. In the end, we used a also well-known data sets for reviewer recommendation, and we compare some methods that were developed by us. So basically, those four here with the method RefFinder. That was state of the art at this point. And in the end, in terms of accuracy at K, basically, and MRR, basically we are better than other approaches like RefFinder or ReviewBot. The only difference is here, where on OpenStack the accuracy is lower for our method compared to accuracy at 1, 3, 5, and 10 compared to RefFinder. But on other projects we actually beat the results. And in terms of time of computation, we actually improve handfully. So basically, our method is quite easy on the computational side, and it can be easy implemented inside real systems. And compared to the RefFinder, which was the state of the art, we actually take some small fraction of time to compute and to be ready to recommend reviewers. So yeah, finalizing this part. Basically, we developed quite fast method that's basically based on the Tversky index that basically beats all other approaches, with the exception of OpenStack, where we have where actually we don't have improvements on the accuracy. Only the accuracy is lower compared to one model. But the precision recall, F measure, and MRR are actually higher than the other methods. So basically, we improve the results in most cases. And yeah, also for this one, we have this was published in 2018, and we have source codes and experiments available at this repository here. And to finalize this talk, we have prepared already 2 papers. One paper is about using ChatGPT in the software development process. Actually, it's a study on another study on a data challenge that is on the mining software conference. We still are waiting for the review, but yeah, the findings are quite interesting. So maybe next time. We also have a paper with manually annotated data set for back localization and adversary attacks under review. And we have work in progress on untangled back localization. So future work for the back localization approach. And we also have some preliminary work done on adversary attacks on large language models, so like ChatGPT or Copilot that are valid. And the idea here is to look for adversary attacks on those kinds of systems. So thank you for your attention, and I will happily answer your questions.
Thank you. And now it's time for questions.
I think so maybe I can start.
Yes, please.
Well, first of all, congratulations for being so brave, because this is an extremely complex area. And it's not that many, deeper papers that go into this. You've shown this relations between the number of people working on the software and the bugs and etc. I thought actually the size of the project is of course very important. So if you just look at the let's say it was here, yes, the number of authors, yes. So if we just look at the large number of authors, it's usually very complex software.
Yes.
So I would rather like to see the relations between the complexity of the software, or at least the size, and the number of authors, because that will just maybe be more relevant than just the number of authors. If there is a small program, the number of authors is usually very small.
Sure, but actually before as you can see, the number of files. So basically, number of files I can tell you something about the complexity of the project. And basically, before our research, people usually said that basically the number of files is the most important factor, so to measure the complexity. But actually, when you look at the DXY here, in terms of the fixing of the bug, so when you look at the DXY here, basically it's not that high compared to number of authors or number of core authors. So actually, the number of people involved is more important in this terms than just the because I would intuitively say the number of files or the number of lines of code says something about the complexity. But in terms of fixing the bug, actually is the number of people that it's more important.
Well, this actually doesn't show that much difference. I mean, there is a bit difference between the blue lines and the other lines. The other lines show it much, well, shows much larger difference. Anyway, I'm very curious about your finding about the GPT influence, because you've just mentioned that it's under review, but can you comment on that?
So yeah, basically, maybe one interesting part that we found is we actually measure. So maybe some context. So basically, we had a data set where we had conversation of developers with ChatGPT stored, and we tracked down in the repositories actual changes that were connected to those conversations, and then we analyzed the impact of the conversation on the actual code that went into the repository. So basically, one of the interesting parts was that changes that were inspired by ChatGPT actually were usually changed faster compared to changes that were not inspired by ChatGPT. So if we had like a commit, and the commit was 50% of ChatGPT and 50% of manual code, actually the lines that were written by ChatGPT were inspired. By inspired, I mean that they were similar in at least 60% or more to the actual lines from ChatGPT, and usually it was closer to the identical lines. So usually those lines required some form of fixing faster than manual lines. So basically, it was like the lines that were created but ChatGPT needed more maintenance after. So basically, it can help with developing the software, but in the end, you will have to pay the debt at some point because they had to like fix the lines. We didn't go into the details about what type of fixes were in the lines. We just spotted that, okay, this line was generated by ChatGPT and it needed like 10 days before it was changed before. And we used a similar trivial analysis. This was like one of the aspects that we measured. But there were some other aspects in terms of projects that we observed. In many cases, people that actually said that, okay, I use ChatGPT for that because this was what we actually could see. Use it for small projects, and usually they were like small homemade projects, not some big projects. If it was used in the of course it can be a bias of the data set that we got, but basically in terms of bigger projects, in most cases ChatGPT was used inside discussion. So basically, it was not used for generating the code, but it was used inside the code review. So people use ChatGPT to generate examples, counterexamples for the code, and use it in the discussion. So this was quite interesting also. But of course, we are waiting for the review. It also can be problem of the biased data because the developers actually had to say, okay, in this commit or in this review, I used this conversation, and they had to store the conversation in the ChatGPT open API. And there was a data set that actually gathered all the open links from ChatGPT and cross-references with the GitHub and other repositories. And then we had like the connection between the actual code and the discussion within the ChatGPT.
Well, I mean, it's quite obvious that large projects will be done in-house because big companies are afraid of using it at all. That's one thing. The other thing is that that people are going to specialize these chats or large language models in programming, and that will also change the way the advices are given or the programs are written.
Sure.
So it's still an open area. But that's
Sure.
a very, very interesting stuff that you're doing. So yes, thank you.
So basically, for the large language models, we actually have some ideas with our adversarial attacks. We actually started to like discussing it and so on. So basically, this is something that we try to do. So yeah. So basically, we would like to see how those models are can how they will deal with the adversary attacks, and because I'm rather skeptical about usage of. I know that ChatGPT is basically, or large language models in code completion are actually now here, and we observe it. But I'm still like skeptical about all of the use cases because, and there are some papers that actually show that those tools can sometimes generate, let's say, suboptimal in terms of security code, and this is something that at some point we will have to fix. So this is a hidden cost of using the ChatGPT, but of course it will get better. So it's we try just to see how it goes.
Okay.
Are there any other questions? So I will have a question. So here we can see the a curve of vulnerability error, let's say survival, yes?
Yes.
And can we see how embargo affects the curve? We should somehow expect that till the embargo, it will fall faster, and then let's say something slower, we can see some.
Sure. So basically, I don't think I have this one here in the presentation. We had like strict limit on the number of pages, but we actually calculated it. So I can look for it for you. The problem was with the embargo, and the reason that we didn't include this plot in the paper and the discussion is basically that with embargo, just a moment. So with the embargo, it's only for some of the commits we actually could spot the embargo. So then we would have to exclude this one because this part probably there was no embargo, but we are not sure because we don't have means to actually check if there was an embargo or not. So basically, there was a difference. I think that. If I recall correctly, what we observed it was that most of the fixes, and you can actually see here, were fixed very fast, but within the embargo. So basically, this is like during embargo, but basically it was like fixing, I don't know, 20 something days within the embargo, but I don't have the plot here, so sorry.
Okay, I think the problem also can be that, embargo is not fixed in different projects. It can last different period of time, and then we have to rescale it to compare it to have some statistical data. Yes.
Yeah, and the problem is that embargo is something, it's not something automatic. It's not something, that there will always be 100 days or something like that. Mm-hmm. For each project, when there is someone calls, okay, I found a bug, the people discuss with the developers. So the CD people in the CD organization discuss with the developers. Okay, do we go into public with this now, or do you need some time to fix it? And if so, how much time do you need? And there were cases where 100 days was not enough, and there was like half a year, 1 year before the fix was valid. But in the end, it's the right direction to publish at some point, because otherwise there are other people that probably know about this bug, and people are not, they do not know that, okay, my software is actually vulnerable. And so the idea is, okay, we will give you embargo, and then published. But yeah, it's the embargo is like something very dynamic, and it's per bug, discussed per bug. So basically, we just try to estimate if it was embargo because we just looked at the publication date, and then we looked for occurrences of the given CVID before the publication date in the repository of repositories and so on.
So thank you. Maybe now someone has another question. Okay, so I think we are run out of questions. So one time, thank you very much. And I invite you for next seminar for invitation email. Okay. Thank you.
Thank you very much.
Bye.
Thank you. Bye.
Bye.
Bye. And I will have a question after.
Okay. So